presentation for the second physics lab. This lab shows how the position versus time, and as well as the velocity and acceleration would be for a dropped object. The two physics principles that I used to explain the phenomena in this lab are the second law of motion and drag force. I showed the position versus time of a dropped object experimentally, and I also compared this data to two computer models that were meant to predict it. As a preview of the results, I found a close match between the drag model and the experimental data. The physics principle I used was the second law of motion, which is basically that force equals mass times acceleration. I used this to show how a net force from gravity or weight force would mean an acceleration for a dropped object. And this acceleration would result in the object speeding up, specifically a quadratic increase of position with time. And I assumed for the model without drag that there wasn't any force other than weight force for the object. The second physics principle I used was drag force, and this is a force that opposes motion experienced by any object moving through a fluid. In this case, the object sticker moved through the fluid of air, and this resulted in a force opposing its velocity, and it squared with the speed. And that would be because I assumed that the drag was turbulent, and this would eventually increase to equal weight force, meaning that net force would become zero, at which point the object would be traveling at its terminal velocity. For the experiment, I used a laminated sticker that I dropped from the top of my wardrobe at around standard temperature and pressure. I released it from rest, I didn't throw it down, and the position of the sticker was identified using tracker software at 1/60th second intervals. For the coding, I used Python to make a mathematical model for a dropped object with gravity, as well as with gravity and drag force. So I used two models. For gravity, I used 9.8 meters per second squared. And for the mass, since I didn't have a scale, I just put it to 1 kilogram. This was also done at 1/60th second intervals over 3/4 of a second. And the initial position was 1.58 centimeters, which I took from tracker data at equals 0 seconds. And for the second model, I found the proportionality constant by using trial and error to make the final position for the drag force model match up with that of the tracker data. Here is the graph of three different positions versus time. As you saw, there was a discrepancy between the experiment and the model without drag, not so much between the experiment and the one with drag. And the experiment and the drag model appeared to stop accelerating towards the end of the period, whereas the model without drag had a constant acceleration all the way through. All three followed about the same quadratic increase in position from 0 to 0.4 seconds, but after that, the model with drag and the experiment seemed to have a relatively constant velocity, whereas the velocity of the model without drag kept on increasing by a constant amount. The experiment most closely matched up with the drag model, which predicted it more accurately, and the experiment likely has, therefore, drag force in addition to weight force, unlike the first model. And this magnitude of the drag force approached the weight force in the experiment and the model without drag, which resulted in zero net force toward the end, and therefore no acceleration and constant velocity. Sources of error could be an accurate identification of the position with tracker, which would be random error, as well as the tracker time intervals not matching up perfectly with the model time intervals, which would be systemic. I concluded that the drag model was a better predictor of the motion in the experiment. And that was because the model without drag overestimated the acceleration towards the end because it didn't have drag force to lower the acceleration. And additionally, the sticker experienced a net force according to the second law of motion up until around 0.4 seconds, after which it seemingly had no net force, which is likely due to drag. So for the question of does either model predict the terminal velocity, the drag model does, because the velocity starts to approach a certain value as time increases, whereas the one without drag had a constant acceleration and velocity always increased. Additionally, if the sticker was thrown downward, would the terminal velocity be the same? They would be, as you can see in the two graphs, which is around 4.05 meters per second.